Hi, in this video we are going to talk about collisions, so let's get started. Okay, we have been discussing that we have the key space with key 1, key 2, key 3 and so on, and we would like to map with the help of the hash functions these keys to array buckets or array slots. And okay, what is a collision? A collision is when we map two keys to the same bucket. If the hash function is perfect, by the way, then there are no collisions at all, but it's very hard to construct a perfect hash function. Okay, so basically a collision when the key 2 and the key 3 are mapped to the same array index, the array index 2 in the illustration. Okay, so how are we able to resolve collision? For example, the first method is the so-called chaining. We store both values at the same bucket. So we use linked list to connect them. So for example, we have a key 1, it's going to be mapped to the index 0 with the value. Okay, what about the key 2? It's going to be mapped to the m-2 index. What about the key 3? It's going to be mapped to the same index, so the m-2 array index. It means that there's a collision. Okay, and we can solve it with the help of a linked list. The value in the m-2 index is going to store a value, of course, we store in this index, and a reference pointing to the next value, because we have to store two values in this case because of the collision. So this is the so-called chaining method when we use linked lists in order to store items with the same index. Another method is the so-called open addressing. It means that we generate a new index for the item. So for example, the key 1 is going to be mapped to the array index 0. Okay, what about the key 2? The key 2 is going to map to the array index m-3. Okay, the key 3 is going to be mapped to the same index, so the array index m-3, which means that there's a collision. We would like to store two values in the same array index. Okay, we have been considering chaining, so we could use linked list in order to store two items in the same array index. But another solution is the open addressing, that we generate a new index for the item because we have come to the conclusion that this array slot is not empty. Okay, so for example, we consider the next array slot available, which is the m-2 index. Okay, so just to summarize again, what about collisions? We can solve the collision problem two ways, chaining and open addressing. Collision resolution with chaining when we put multiple entries into the same slot with the help of a linked list. If there are many collisions, then the order 1 complexity gets worse. Why? Because the worst case scenario when we map, so we generate the same index for all of the keys. It means that we are going to end up with a linked list because we have to store all the items with the same array index, so there will be basically a linked list. And for example, if we want to find an item in a linked list, it's going to take order n linear time complexity. It is definitely not order 1 constant time, so that's why this chaining is not always a good solution. And of course it has an additional memory cost due to the references. Okay, what about the other solution, the so-called open addressing? It's a bit better solution because if collision occurs, we find an empty slot instead. We have several algorithms. The linear probing, if a collision occurs, we try the next slot available. If there's a collision too, we keep trying the next slot until we find an empty slot. Okay, so for example, we have a collision at the index 5. Then we check the index 6. Okay, if it's not empty, we check index 7. So we keep considering the LA slots in a linear manner, one by one. What is the quadratic probing? We're trying slots 1, 2, 4, 8, 16 and so on units far away from the collision. This is the so-called quadratic probing. And then basically, and one of the most important open addressing technique is the rehashing. we hash the result again in order to find an empty slot. So we end up with an array index that's not empty, then we are going to use the hash function again. So this is the so-called rehashing. Okay, so we come to the conclusion that the space complexity is going to be linear, of course, because we have to store every item, no matter it's an array, it's a linked list, or it is a hash map. Of course, it's going to be ortho and average case and worst case scenario. What about the search, the insert, and the delete operation? We have come to the conclusion that associative arrays with array underlying data structures is going to be very fast on average. So it's going to have ortho 1 constant time complexity, because we are going to use the hash function to generate array indices and so on. We are able to do it in ortho 1 constant time complexity. But a worst case scenario is going to be linear, which is worse than the balanced binary search tree ortho logarithm time complexity. So that's why basically, okay, we know for certain that we can do better than binary search trees, but we have to make sure that these algorithms are going to be okay. What kind of algorithms? For example, constructing the hash function, or how to solve the collision problem with the help of open addressing or chaining. Okay, we come to the conclusion that open addressing is a better solution, so we definitely use open addressing. But that's why we have to find a good algorithm, because the worst case scenario is going to be linear. And we have discussing balanced binary trees where the worst case scenario was ortho log n, so logarithmic time complexity, which is better than linear time complexity. So that's why, okay, on the average, these associative arrays are very efficient, but we have to make sure that the underlying algorithms are working fine. Thanks for watching.